Hello, Rouse. For supplement to lesson 1.4, I thought I'd just go through the solutions to this worksheet here, sort of dictating our thoughts. It says to use the graph of this figure down here, here's the graph of f, to answer the following questions. So one of the things that we want to talk about here with this new notation is the difference between behaviors versus limits. These expressions are asking us, do these limits exist? And if they don't, then we should probably scratch out the equal sign and write a different conclusion. But these right here are just behaviors, and it's impossible for a behavior to not exist as long as the relationship exists near those values, if these target values are inside your domain. So for example, you should be familiar with behavior notation from advanced functions. This question is basically saying, as x approaches values of -12 from values that are smaller than -12, what are y values converging on? Let's take a look. As x values approach -12 from values that are smaller than -12, my y values are getting closer to 0. I don't need f of -12 to equal 0 for this to be true. What happens as x approaches -9 from values that are larger than -9? Looks like my outputs approach 0 again. So here's a case where the f of -9 doesn't equal 0, but I don't care whether it's a solid dot or a closed dot because it's just a behavior. I'm getting close to 0. As x approaches 5 from values that are smaller than 5, where's 5? Looks like, I'm sorry. Oh, 5. Here we go. As x approaches 5 from values that are smaller than 5, looks like my outputs diverge towards positive infinity. So I'll use that symbol right there. As x approaches -9 from values that are smaller than -9, looks like my outputs are approaching -5. As x approaches -6 from values that are greater than -6, looks like my outputs are approaching 5. As x approaches 0 from values that are greater than 0, looks like my outputs are approaching 2. As x approaches -6 from values that are smaller than -6, looks like my outputs are approaching 5. As x approaches -3 from values that are greater than -3, this is a little bit weird because like I don't feel like my values are approaching. They're just sort of constantly remaining at 1. This is still the comment that we should make. The limiting value of the behavior, let's say, is 1. As x approaches 2 from values that are greater than 2, looks like my outputs are approaching 3. As x approaches -3 from values that are smaller than -3, looks like my outputs are approaching 1. As x approaches 0 from values that are smaller than 0, looks like my outputs are constantly at a height of 1. So that'll be the correct conclusion there. As x approaches 5 from values that are greater than 5, looks like my outputs diverge towards negative infinity. As x approaches -12 from values that are greater than -12, looks like my outputs are approaching 0. As x approaches 2 from values that are smaller than 2, looks like my outputs are approaching 3. Okay. Now, for these limits to exist, what we need to see is convergence. We need to see the function outputs approaching the same finite value from the left and from the right. So we can look up here and see if we could find a left side behavior and a right side behavior and see if they're converging to the same finite value. And if they are, just put that number in here. Let's try it for a couple of these. As x approaches -12 from the left, the value of the behavior is 0. As x approaches -12 from values greater than -12, the function values approach 0. Therefore, the limit exists and the value of the limit is 0. But I mean, we probably could have just done that on the graph as well and seen, look, as x gets close to -12, my outputs get closer to 0. Or say it this way, you want your function values to get closer to 0, all you would need to do is substitute in inputs that get closer to -12. Okay. As x approaches 5, well, first off, my behaviors are different, and second off, they're not even converging on the same number. So I'm going to scratch this out and say it does not exist. What I want to cover here that might not have come up in the lesson is that if I give you g of x equals the reciprocal of x squared, g of x is going to look like this, right? You'll have a horizontal asymptote of y equals 0. An even type vertical asymptote, your outputs will never be negative. So I would say that the behavior as x approaches 0 from the right of g of x is this symbol. The behavior as x approaches 0 from value smaller than 0, I would use this symbol. Those symbols are the same, but they're not the same number. They're not a number. You're not converging on a finite number. You're just diverging in the same direction. And therefore, I would conclude that the limit as x approaches 0 of g of x does not exist. Okay, it has to be, the behavior from the left has to be the same as the behavior from the right, and they both need to be converging on a finite real number. Okay. Around -3, we are converging on 1. Around -6, we are converging on 5. Around -9, there is not convergence. The value that I am approaching from the right is different than the value that I'm approaching from the left. They're both finite values, but they're not the same finite value. The behavior as x approaches 2 exists, even though f of 2 doesn't exist. This is very important for us in lesson 1.5. The limit as x approaches 2 of f of x in the general case is not equal to f of 2. This is often going to be true, but I'm not going to write it down if it is often true. I'm going to write this down because this is not true in the general case. In this specific case, it's not true. Okay, so you're not just substituting in x equals 2 when you're evaluating a limit. Okay, f of 2 does not exist. F of 2 is not defined. 2 is not in the domain of f. That doesn't cause any problems. You want this function to get closer to an output of 3? Well, I mean, you could just put in some other input over here. You want this part of the function to get closer to outputs of 3? All you would have to do is substitute in inputs that are closer to 2. And because that's the case, we would say that the limit as x approaches 2 of f of x exists and is equal to 3. Okay. As I approach 0 from the left and 0 from the right, I am not approaching the same finite numbers, so that does not exist. Okay. And that means that up here there were, what, 14 behaviors. All of those behaviors exist. I can come to a conclusion about all of those behaviors. Out of these 7 potentials, there were only actually 4 limits. Okay, these limits do not exist, or the limit does not exist here, so there is not a limit. And then we can still use behaviors with this symbol. This is definitely not a limit because we need x to approach a finite number as well. But we'll often read the limit as x approaches infinity of f of x. I'm not super happy about any of that language, really, because it's not a limit and x doesn't approach infinity. I would try reading it as a behavior. The behavior for your outputs from f of x as x increases without bound is that they are going to converge on 0. So I can write that statement just like how in advanced functions I could write as x grows without bound, y values approach 0. I probably would have included the direction in advanced functions, but we just don't have to do that anymore with limits. Okay, focus on the ideas. There's some communication opportunities here, and often students get a little bit bogged down by trying to memorize. Focus on developing these ideas, and I think you'll do better.